All right, so you'll notice in WebAssign, I believe I have assignments listed up there for sections 2.5 and 2.6. Hoping to come back to section 2.5 later on in the semester when we talk about eigenvalues and eigenvectors and long-term behavior of different things. That is also associated with what's in section 2.5. Perhaps we'll get back to section 2.6, but my guess is we probably won't. Maybe we'll get back to that section, but moral of the story, we're not doing 2.5 and 2.6 right now. Okay, so those will be sitting in there listed as assignments, but they won't be assigned now. Okay. The next assignment we'll do, we're going to skip ahead to chapter 3 and start talking about determinants. As you may have guessed by the handout that I just gave you. Okay. So I start this off a little bit differently than what you'll see in the textbook. Oh, because I hit the wrong laptop button. That's why it's not on the screen. Found this in, this was several years ago, but I found this in an old publication from Dover Publications. If you're interested in math or science volumes that are really cheap, Dover publishes old volumes and puts them out in paperback form for like $10. So every once in a while you come across something that's really, really good as a presentation tool to understand what we're even trying to do from the standpoint of a calculation that we're doing with a matrix, in this particular case, determinants. Every once in a while you'll come across a really good explanation of something that you'll want to pull that out. I don't know why. Does they hand out an extra one to something?
There's one.
Ah, wonderful.
Thank you.
Here we go. I had printed 14. We'll just leave that for hope. Thank you. All right, good. I was really worried because I thought I printed out 14 and I handed them out and I was like, you have one left over and 2 people missing. All right, anyway. Where was I? I forgot. Anyway, the whole point of this was, this isn't in the textbook that we're currently using. It's not how this is presented to start with, but I think it's a really good introduction to understand a quote unquote physical quantity that we're hoping to compute based on determinants or matrix. Okay. All right, so that's why I do it this way. So rather than making you buy an extra resource just for one thing, I just typed up a little handout to go along with it. Okay. All right. So let's start with an n by n matrix. And we can think of this matrix broken up into rows. So each row represents a vector in Rn. So when I say Rn, I mean real vectors where you've got n components. So R2 would be 2 components. Each component is a real number. We associate vectors in R2 a lot of times graphically with they start at the origin and they end at a point, right? R3 is 3-dimensional coordinates. So again, same idea. Start your vector at the origin, go out to the point in 3 dimensions. That's your vector. We're going to extend that to any number of dimensions that we want. So what we have here, if we think about A as being row vectors, I've got n vectors, each of which live in Rn. Hopefully they create some sort of an object, physical object, but again, in n dimensions, what physical object doesn't make much sense. But if we think about these as a physical object, in n dimensions, we refer to that as a parallelepiped or a parallelepiped, depending on whether or not you want to pronounce the ed on the end or not. When I learned it, I pronounced it. So you'll hear me say parallelepiped, you'll hear other people say parallelepiped. Doesn't matter. Okay. The idea is that all of the faces of the object are parallelograms. Okay. So here's a parallelepiped in 2 dimensions, or a parallelogram that you're used to. So here's the A matrix 2, 1, 1, 3. So we're treating the 2, 1 row as a vector 2, 1. So again, we can plot the point at 2, 1. I'll do it in this left one first. Plot the point at 2, 1. Draw the segment out. That's a vector, the vector 2, 1. Do the same thing for the second row, vector 1, 3. And if you've done anything with vectors in any other class, you've probably talked about adding them graphically. So you create the parallelogram so you can do the sum of them and go across the diagonal, right? But all we're doing here is, say, take a carbon copy of the 2, 1 vector, draw it at the tip of the 1, 3 vector out, and make it parallel. Because again, vectors aren't changed by translation, right? You can slide them wherever you want, but don't rotate them or stretch them. Once you rotate them or stretch them, that changes either direction or magnitude, right? But if you just slide them, that's okay. So vectors are invariant under translation. All that means, fancy words for, I can slide them wherever I want, and I don't change the vector. Okay. So again, we're sliding up this vector here to here, making those sides of a parallelogram. Same idea with the other vector, sliding this one here to here, and making a parallelogram. That's what it looks like in 2 dimensions. I can try to draw one of these in 3 dimensions, but it's going to really be nasty. But if you wanted a really easy parallelepiped in 3 dimensions, a cube would work, or any type of rectangular box would work, okay? Because rectangles are parallelograms, right? So if you think about your normal rectangular box, you can think about 3 vectors in your box. I could have a vector here, a vector here, and a vector going up, right? And then just make carbon copies here, 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 here. You know, that was not a very much good of a carbon copy, but same idea, right? Make a box. This is why I didn't try to draw it with parallelograms. Those aren't even rectangles. Okay. Anyway, that's all we mean. So in this case, you would have a 3x3 matrix. Each of these, you'd have 3 vectors that would be coming out, and then you make the carbon copies in the appropriate spots and make a box. If you can envision doing that in, say, 7 dimensions, you've got a more vivid imagination than I do. All right. So the idea here is that we want to come up with a function that calculates the volume. Now, in 2 dimensions by volume, we mean area. But that's our goal here. We want to create a function that gives us volume, or at least a way to calculate volume. The way we're going to define the determinant function, it's possible we can get negative values out, right? But we can take, much like what you've done in calculus, where you've done area under a curve, take the absolute value of it, that gives you the area under the curve, right? When you do the definite integral, if it goes under the x-axis, it counts as a negative. Same idea here. If you're thinking about this as volume and it pops out as a negative, you just take the absolute value. You may have done this if you've done cross products in Calc 3. The magnitude of the cross product of your vector gives you the area of the parallelogram defined by the vector. If you've done scalar triple product in Calc 3, where you do the cross product of 2 vectors and then dot product with a third, you have to do the absolute value in that case to get the volume of the 3-dimensional object. If you haven't done that, you can ignore all the words I just said, okay? But same idea. When you do magnitude of a vector, that's going to be positive. Turns out magnitude of your cross product gives you area of a parallelogram. And if you do that scalar triple product where you do A dot B cross C, if you've seen that notation in Calc 3, that gives you the volume of the 3-dimensional object determined by A, B, and C, but it might be negative into absolute value. Okay. Anyway, it's the same kind of idea that you talk about in calculus, right? If it turns out to be negative and you want to attach it to a physical quantity, you take the absolute value. Okay. Anyway, that was a lot of words for that particular idea. All right. So again, if I want to write this in function notation, the idea is that I want a function. The name we give the function is determinant. We abbreviate it with DET. We want it to go with a domain of the set of n by n matrices. And so right now I'm writing this. I don't need to cross in there, I guess. Sorry. I'm trying to give you some new notation that we're going to see in the next chapter. When you write M, we're talking about set of matrices. The subscript here is going to have 2 components to it. One's going to be the rows, one's going to be the columns of all the matrices in there. Okay. So this is talking about the set of all possible n by n matrices. All of them are squared. Okay, so that's the notation. That's going to be the domain of our function. What we want to get out of this is a real number. So your codomain here is going to be the set of all real numbers. This is our function notation. Just going through the different notations so that when we use it later, you'll be familiar with it. Okay. When I write a name out in front, that's just the name I'm giving the function. In this case, again, we're calling it the determinant function. We abbreviate that DET. And pretty much any computer program that you use that will calculate a determinant has that for its notation. Domain is the first set that we write down. That's the things that you're going to plug into your function. Codomain is the second set that we write down. That's going to be the things we get out of the function. And the arrow just means that we're plugging something here, doing something to it, and getting something here. If you've had discrete, you've seen this notation. If not, I'm just telling you what the notation is because we'll use it later. All right. So let's think about some properties that this function should have. So the first thing, notice that I've taken the matrix A. What have we done to matrix A? Matrix A was, oops, I gave it the same name. It's just that we have a new name for it. The new matrix was the same name that I gave it. Doesn't matter. Looking at the matrix 4, 2, 1, 3 and the original matrix that you had on the first page, what did I do? Yeah, multiply the first row by 2, right? I mean, basically, if I think about it in terms of the picture, if I take row 1 and multiply it by 2, what did I do to the vector that I represented with the vector 2, 1? What did I do to it? What does multiplication by 2, what effect does that have on your vector? It doubles the magnitude, right? It makes it twice as long, correct? When I multiply it by 2, it makes it 2 times as long. So that's all I've done here. I can see I've got the, here's the 2, 1 point that we had originally. Here's the 4, 2. And you can see that that vector really is 2 times as long, right? Now I drew in the other helping lines in here. This one is the original area, right? That's the original parallelogram. What can I say about this parallelogram that I just colored in red, and this one now that I'm shading it in black? What should those areas be in this case? They should be equal to each other, right? Because basically all I have done is just taken a copy of the vector 2, 1 and stuck it on the end, right? And made another parallelogram. So relative to the original area, the area of the new parallelogram we just formed is what? Is twice as big, right? So we notice that the area of the new parallelogram so I can spell parallelogram, that would be helpful. That area of that new larger parallelogram is twice that of the original. Twice the area. What did we do to the row again? What do we do to the row 1 relative to the original matrix? Multiply by 2. So notice we multiplied the row by 2. It made the area twice as big. And if we think about this in terms of physical quantities again, if we're thinking about wanting to determine it in some sense to give us a volume, then multiplying one of your vectors by a constant changes that dimension by that constant, right? So it's changing one of your lengths by that constant, so it should make that volume change by that same constant amount, right? So for example, if you took a rectangle and you tripled its length and left the height the same, that would triple the area, right? Same idea. Now notice if you start changing multiple rows, multiple dimensions, it's going to change it by each of those factors, right? So you have to do it a row at a time. And we're going to see that when we start talking about properties and determinants later. But what I've done at the bottom here is basically summarize what I just said. Okay? Notice here at row I, we've multiplied that row by a constant. I refer to the constant as gamma. The letter doesn't matter. I've just multiplied that one row by that constant. You just told me that in general that should change that one dimension by that factor. So it should change the volume by that factor, right? So if I want to do the determinant of the new thing, that should be that constant times the determinant of the old thing. And what it looks like basically is that you're pulling a constant out of the determinant function. Notice it's not over the entire matrix, right? That says it's one row at a time. If you had a gamma here at row I and a gamma at row 1, I'd have to pull it out twice. You have a gamma squared out in front, right? If I did it to every single row, I'd have to have a gamma to the n out in front. Okay. So be careful. Mainly what I mean by that is if you've got the determinant of a scalar times a matrix, it's not just simply pull the scalar out. Because this scalar gets multiplied by absolutely everything, right? Which means that C gets multiplied by row 1 and row 2 and row 3 all the way down to row n. So what should I put on this C to make this a true statement? An n power, right? Because I got to pull out a C for every single row. This is a determinant property. This is a valid determinant property. But it's very, very tempting to think of things as everything being what we refer to as linear, right? Constants move in, constant moves out. That's great, right? Those are very special functions. You don't know, even though you try to do it, you don't know of very many functions where you can just move the constant in and out and it work, right? It's what you want it to do, but doesn't happen very often. Okay. So here, be careful. If you've got the determinant of a constant times a matrix, yes, you can pull out the constant, but you have to do it n times. Where n, again, is that n by n matrix. It's how many rows you have. Okay. Right. Again, we get this property basically because of this property that we want the determinant function to have. We want the determinant function to give us a volume in some sense. And we're changing one dimension, in this case, by that constant factor. So it should change the volume by that same constant factor. So far, so good? Okay. All right, so what else might we want? Let's look at the next page. Okay. This one says, what happens if we add a vector to one of the other row vectors? Now, you might notice what I'm trying to do here. The original one that I did, I'm trying to relate this to stuff that we've already done. The original one we did was we took a row times a constant. You should recognize that as something that we've done. This is on your last test, right? This now says we want to add a vector to one of the other row vectors. Well, we've taken a vector or a row and added it to another row, right? So what we're doing right now is we're running through the elementary row operations and seeing what effect it has on the matrix, how to determine. Running through those different things. That's what we're doing. Okay, number 1. Students get confused by this because of the dashed line. This is not a 3-dimensional picture. This is a 2-dimensional picture. This is in R2. It's on the plane. Okay? Okay, so I know with the dash, it looks like it's supposed to be 3D, right? You've got some sort of a triangular prism, right? There's a triangle on the bottom, a triangle at the top. That's not what this is doing, okay? Okay, so the original picture is this one I'm going to outline in red. Here's your original one, okay? So this the one I have in red, and I'll actually write it in red, that should be the determinant of the matrix that just has the two rows R1 and R2. So the one I have in red there, that's why that is drawn out in red. Okay. This one, I'll try a different color. Hopefully the colors help. I don't know how well you can see them up on the screen. Oh, that's pretty red. I'll try green. Let's look at this one. What are my rows going to be for this vector, for this parallelogram that I'm trying to figure out the volume of? What two vectors are making up that parallelogram in green? R2 and V, right? I'm going to put the R2 on the bottom just because that's where I have it in the other one. I'm going to make it match. Okay. Now the last one. Let's make one more color. And just for fun, let's make it a sparkly color. This one's got all sorts of different sparkles. Let's go this way. There's one advantage of playing on the computer. I get to use different colors that I wouldn't be able to use on the board. All right. Sparkle parallelogram. Well, certainly one of the vectors we used is what? What's the easy vector that we used? The R2 again, right? That's giving me this side here and this side here, right? Okay. I need to figure out what the bottom one is, but this is, again, if you've done vectors graphically, and I'm just drawing over this again and changing the star pattern as I do it every time. That bottom piece here, graphically, what vector is that? It's R1 plus the V, right? Okay. So this first row would be R1 plus V. All right, change out of sparkle mode. All right, so this is what I mean by what happens if I add another vector to one of the rows. Notice I've taken the original matrix, which is the red one that I wrote, right? And I've added the vector V to just one of the rows. That's where we got the R1 plus V. Okay. What I want is a relationship between these three quantities. Well, let's see if we can figure it out. And to help us figure it out, I'm going to erase all of these colored lines that I just put in here. Okay. I think it'll be helpful to get back to where the original start here. Okay. Again, I told you this wasn't three-dimensional. However, it's two-dimensional. But however, there are some properties that we'll notice. If I look at this triangle and this triangle, what should be the area of those two things relative to each other? Okay, that's how we calculate the area of a triangle, generally speaking, but relative to each other, what can I say about the areas? They should be equal, right? Notice it's the same vectors that form the triangles, right? Okay. All right, so notice that if I take that first parallelogram and add it to the second parallelogram, that contains this triangle, right? But this is this one. What happens if we do it the other way around and look at the big parallelogram that has the two dashed lines? Well, it contains that triangle, but this is that one, right? So using the fact that you just told me that these two things are equal to each other in terms of area, what can I say about the area of the parallelogram determined by R1 and R2 and the area of the parallelogram determined by V and R2 added together relative to the big parallelogram with the two dashed lines? What should be true if I add this one, R1 and R2 parallelogram, in the R2 and V1 to the big parallelogram. Or sorry, relative. Try that again. If I take the two smaller parallelograms, what's the area? What's the sum of those two things in terms of area going to be relative to the big parallelogram? Yeah, they should be equal, right? Because again, notice when you take the two small ones, I include this triangle, right? When I take the sum of the big one, I include this triangle. You already told me they're the same in terms of area, right? And they both contain the area that I didn't shade in. Okay? So the moral of the story is that if I take this first one and add it to the second one, I should get the third one. Basically, what really we want to think about it kind of in the reverse order, if you will. Right? It looks like I've split it up as a sum. But notice that the R2 didn't change, correct? We agree? Okay. All right, so that's what the in general part means at the bottom. Notice that what we have in the bottom, these rows here that I'm putting brackets around are the same all the way across. Nothing else changed, right? Those things that have brackets across aren't changing, okay? I'm splitting up the determinant over a sum in a single row, okay? Not the sum of two matrices. It's important, very important, that you don't try to split up a sum in general. There might be some specific matrices that works for. If one of them is a zero matrix, for example, it works. But generally speaking, you cannot break up a determinant over a sum. Again, notice what the formula, notice what the equation that we have looks like. The rows from 1 to I minus 1 and I plus 1 to n do not change in any of the three matrices. The only row we've done anything on is row I. Okay? We have not added matrices together here, unless these row vectors all happen to be zeros. Okay? So again, there are special cases, but generally speaking, this is not true. All right. Well, let's ask the next question. What happens if two of the row vectors are exactly the same? Well, think about it in terms of parallelograms again. If you have your matrix A is, let's just, for example, say 1, 2, 1, 2. Two rows are identical. If the two rows are identical to one another, well, that says you would take the vector 1, 2, draw for the first row, and then draw on top of it again for the second row, wouldn't I? I didn't create much of a parallelogram, did I? What would the volume or area in this case, since it's two-dimensional, what would the area of that parallelogram be determined by the exact same vector landing on top of itself? 0, right? There is no area there. Okay. So that determinant would be 0. Wouldn't have any area at all. So notice again what I've got for the general rule typed up there for you. I've got some rows leading up to row I. I've got some other rows in the middle, don't know what they are, but later on I see the exact same row that I saw before. Identical rows here, right? If I see identical rows, I know for a fact that the determinant is 0. Because again, if we think about it in terms of what we just talked about as a physical quantity, if you've got one row giving you one dimension of it, right? And then you got another one that lands right on top of it, you didn't give it any volume at all. You've collapsed it down a dimension, at least a dimension. So you get the determinant of 0. So again, if two rows are the same, the determinant is 0. All right. We need a scale. We've actually got enough information here to compute any determinant of any matrix that we would want. We've got enough information to do that. Okay? What we don't know is, well, where do I start? I need a scale. Well, the scale that you would use in any dimension is what you would think it would be. So what if I started with 1, 0, 0, 1? Well, 1, 0 is that vector, and 0, 1 is that vector. If I make the parallelogram, what kind of special parallelogram did I just draw? It's a square, right? What are the side lengths of that square? 1. What area would you like that square to be? 1. Wonderful. Okay. So this is how we pick our scale. This side length has length 1. This side length has length 1. I made a square. Great. Area of the square with one side length of 1 should be 1. Right? Look at my matrix. What special matrix did I write down? The identity matrix. It's a 2 by 2 identity matrix, right? Generally speaking, you could bump this up more dimensions, and that's why we're using the determinant of the identity matrix to be 1. That's our unit scale. And that kind of makes sense, right? Because each row in that case is giving you a unit vector in a direction, right? If you think about it in 3 dimensions, 1, 0, 0 is your unit x direction. 0, 1, 0 is your unit y direction. 0, 0, 1 is your unit z direction, and you'd make a unit cube. Same concept, right? Okay, cool. Now we literally do have everything that we could possibly need to compute a determinant function. Here's what's very, very interesting, and we're not going to prove this. But if you show that any other function, no matter how we compute it, if you show that any other function satisfies these properties, it is the determinant function. There's only one function that actually does this, and it is the determinant function. We're going to have another way to help us calculate determinants. This way is going to be doing row operations. You can kind of see that, right? I talked about doing constants and adding rows and those kinds of things, right? Okay. This is going to help us with row operations to calculate a determinant. But there's going to be another way to calculate a determinant that we're going to use, and it has to be equal because they both satisfy the same set of what we're referring to as axioms here, which is really kind of cool. We came up with this idea to say, well, we didn't come up with it. We're talking about this idea. Somebody else came up with it. We came up with this idea to talk about using determinants to help us create a volume function. Turns out there's only one way to do it if it's going to satisfy these properties we've talked about. Literally one way to do it. This is really cool. At least I think it's really cool. You can think whatever you want. I don't care. Okay. All right. In any event, let's keep going. Our next page here is talking about how do we do determinants of elementary functions here. All right, remember our elementary matrices. Well, how do we do elementary matrices? Those are one step away from the identity matrix, right? What did I do to the identity matrix for that first one? Yeah, I multiplied one of the rows by a constant, right? When we say we multiply a row by a constant, what does that do to the determinant? Multiplies it by that constant, right? So this will be, I can think about, basically kind of think about taking that C out, right? Out of that one row. If I take that C out of that one row, what matrix are you left with? I, right? Agree? Okay. And what did we just say? We all agreed that the determinant of the identity matrix is 1. So I would have C times 1. So I'll just write a C, so I don't have because I don't have an extra blank there. We just said the determinant matrix, the determinant identity matrix. Again, the determinant of the identity matrix is 1, so we get C when we're done. So there is a determinant of that elementary matrix has to be C. Okay, what did I do in the next one? Good. I took this row, whatever row it is, right, multiplied it by C, and added it to that row, correct? Okay. So if I think about this again, this row right here is a sum of two things, right? You agree with that? Okay. So I should have put, it's okay. I know there's lots of dots in here. Got lots of dots going on here. Okay. All right. Let me put one more thing in here. Let me put a 0 right here. I can think about adding the two vectors, with a 1 in that second spot and zeros everywhere else. And then I can do 1, 0, dot, 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 0. The next one will be 0, 0, dot, 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 C, 0. I know, lots of dots. Good news is that we're only going to do this once. Okay. I can split that second row. I have it in the second row, but I could arbitrarily put it anywhere. I can split that second row as 0, 1 and a bunch of zeros and add it to a bunch of zeros C and then a bunch of zeros, right? I can split it into those two pieces. We agree with that? Okay. What's that first matrix? It's the identity matrix. What's its determinant? I forgot to write the determinant function on there. Sorry. We'll do that here in a second. What's the determinant of the identity matrix? 1, right? So when you do the determinant of that first matrix, I forgot to write DET in front of this thing because I was too busy writing dots. That first matrix has a determinant of 1. Well, let's do the second one now. Look at these two rows here. Well, from that previous thing, or one of the previous properties we wanted, I could pop the C out in front, all right? Because it would be C, just C times that one row. If I take the C out in front, what do you notice about these two rows? They're equal to each other, right? They're the exact same row, aren't they, if we pull the C out? What did we just say happens to a determinant if they have identical rows? It's 0, right? So this matrix is going to have a determinant of 0. And in general, if you have one row that's a scalar multiple of another row, you're always going to get 0 for the determinant. Okay. So you said the determinant of the first one was 1. The determinant of the second one is 0. The determinant of that is 1 for that elementary matrix. Yes?
What's the one on the diagonal row?
Remember, I'm splitting this vector up into two pieces.
Oh, you're splitting the second vector specifically.
Yeah, that's specifically the second row is specifically splitting it into two pieces. Yeah. All right, so what we notice about that second one is that we don't change the determinant. That's weird a little bit. If I take one row, a multiple of one row, add it to another row, and replace that other row, I don't change the determinant at all. It stays the same. That elementary row operation doesn't change the determinant at all. Okay? All right. So this last one, what did I do here to the identity matrix? Swapped rows, right? So what we're going to do here is see what the effect of a row swap is. Okay? I did it for a 2 by 2 because it's a little bit easier to write down because, well, as you noticed in the previous, I had dots everywhere, right? Here we're going to do it for a 2 by 2, but generally speaking, we can do it for any sized matrix where we swap any sized elementary matrix where we swap 2 rows. Okay, but we're going to do this with the other operations. First thing I'm going to do is I'm going to take row 2 and add it to row 1 and replace row 1. What does that do to the determinant when I take row 2 added to row 1, replace row 1? What did we just say in the previous? Nothing, right? It stays the same. Okay. So that was from here to here. This is row 2 plus row 1 replace row 1. Doesn't change the determinant. Okay. Okay. Now let's do negative row 1 added to row 2, replace row 2. Negative row 1. So again, let me write down what we did here. We did row 2 plus row 1, replace row 1. Now I'm going to do negative row 1 plus row 2, replace row 2. What does that do to the determinant? Nothing. What matrix do you end up with? Good, good. I get 1, 1 on my first row and 0, negative 1 on the second row, right? Next thing I'm going to do is I'm going to add row 2 back to row 1 again. What does that do to the determinant? Nothing. What do I get when I take row 2 and add it back to row 1? Good. By the way, what am I trying to get to by doing all of this stuff? What have I been trying to do? Get it back to the identity, right? Back to our scale, correct? I'm almost there. How is this different from the identity? I got a negative 1 here, right? But I can think of this as a scalar and pull it out in front, right? We agree? Just take it out and pull it out in front. Okay. When I pull it out in front, that changes the determinant by that scalar, doesn't it? So you would end up with, if I do negative row 2, replace row 2, I get negative the determinant of 1, 0, 0, 1. Or, I should have put one more line in there. I get negative 1 at the end. So now we know what the effect of every elementary operation does, every elementary row operation does to a matrix. It changes it by those values. Okay? So when you multiply a row by a constant, it changes the determinant by that constant. When I do a constant times 1 row added to a second row, replace the second row, it doesn't do anything to the determinant. When if I swap rows, it makes the determinant negative. Okay? If you've done things with vectors before, you know that maybe you've done some things with orientation. When you do your cross product, you do kind of the left hand, you do the right hand rule for cross product. This is your first and this is your second. Your third point's up, but if you do it the other way around, you're down, right? Right? Okay, so that's all the negative saying is that we're looking at a different orientation. That's why we would take the absolute value to get the actual volume or area in this case. All right. So this last part is just summarizing what we talked about. If B results from A by multiplying a single row, I'll say row I, by C, then the determinant of B is C times the determinant of A. Multiplying a row by a single constant changes the determinant by that constant factor. Number 2, if B results from A by multiplying row I by C and adding to row J, and replacing row J, what does that do to the determinant? Nothing. Good. The determinant stays the same. Good. Finally, if B results from A, by swapping row I and row J. Oops. Why are you not writing? That's super weird. It's like my pen ran out of ink. What are you doing? Oh, no, that's weird because it's not done that before. That is bizarre. Okay, it thinks it's still connected. Okay. Why are you not drawing? Okay, it still thinks it's there, but it's not doing anything. Okay. Guess I'll write it on the board and talk, so when somebody's watching the recording, swapping row I and row J. Then what's the relationship between determinant of B and determinant of A? Yeah, it's negative of it, right? Okay. Multiplying by the moral of the story here, multiplying the row by a constant changes the determinant by that constant factor. Doing that operation where you take one row, add it to another row, replace that other row, doesn't do anything to the determinant, stays the same. You swap two rows, makes the determinant negative. Right? Okay. So this allows you to go through and calculate. All I'm doing is selecting the thing with my finger. This allows you to go through and calculate determinants through row reduction. Okay? So that's what we'll do next time. It will also give us a nice an added condition. We're going to theoreticals that we're going to add a lot of things to. It's going to get us another condition to that. Okay? We'll get that in there, and then we'll also talk about another way to calculate determinants when you've got lots of zeros in your matrix. All right. Have a good one. We'll see you on Wednesday. If you did not give me your homework when you turned in your test, we'll take that too. So I get that back to you on Wednesday. Have a good one. That's just weird.